Assalamu alaikum wa rahmatullahi wa barakatuhu. Alhamdulillah. Wassalatu wassalamu ala Rasulullah. Amma ba'd. So today we are going to start the chapter 7 from the book of Norman Nice, Control System Engineering. We have already studied the stability of the system in chapter 6 and transient behavior of first order and second order system in chapter 4 and modeling in chapter 2. So once a system is stable, this means that for the bounded input the system output is bounded. Then we talk about the steady state error, and from the steady state error we mean that suppose we have a plant transfer function. G of s is the plant transfer function, and here the output of this system is represented by C of t in time domain and C of s in the s domain. Then this output, if we bring back and here we put some type of controller, this controller can be of many different types, and here plus and minus. So here is the reference input R of t. So to this error signal we say E of t, which is fundamentally equal to R of t minus C of t. So this is the error signal. Now if the closed loop is completely stable, when I am saying closed loop I mean this complete block. If this closed loop is stable, then we can say that the error is bounded, and whenever the system is stable, so the transient of the system die out with the time, and whenever the time approaches to infinity, the transient response behavior also approaches to 0. So in that case, what will be the behavior of ESS? To this we say steady state error, which is equal to normally limit t tends to infinity E of t. So this type of thing we will be discussing in the this series of lecture. This series of lecture consists of 7 lectures. The first lecture is lecture 1 part A and lecture 1 part B, and then from 2 to 7 we will have 6 lectures. And just keep this one point in your mind, that we talk about the steady state performance when the closed loop is stable. When the closed loop is stable. If the closed loop is not stable, then the discussion of steady state error is meaningless, because it will definitely diverge to infinity. So these are the details we will be discussing in this chapter. Thank you very much. The learning outcomes of this lectures are the part of the course on linear control systems ECCE 4416, offered by the Electrical and Computer Engineering Department at Sultan Qaboos University. So according to the topics, the learning outcomes are as follow. In chapter 1 we will be discussing the steady state error for the unity feedback systems, and this first part is the introduction part, where we will divide the discussion into 2 parts. So the introduction lecture will be part 1 and part 2. Then we will be discussing about the specific systems and their steady state performance. Those are like type 1 system, type 0 system, type 1 and type 2 systems. We will discuss them in detail. Then we will be discussing the gain of the closed loop system to meet the steady state error specification. This will be our lecture number 4. Then The steady state error for the disturbance input will be discussed in lecture 5. And in lecture 6, the steady state error for the non-unity feedback systems. All the discussion from 7.1 to 7.5 will be devoted to the unity feedback systems, but in 7.6 we will be discussing the non-unity feedback systems. And the sensitivity of the system we will discuss in lecture number 7. So there are three fundamental requirement for designing a control system. First of them is the transient response of the system. And the transient response, as we discussed, that it is due to three basic things: due to the characteristics of the system, due to the input to the system, and due to the initial condition of the system. And when we say initial condition of the system, it means the energy stored in the system. So one of the requirement that the transient response of the system should approaches to zero without oscillation as quickly as possible, and this requirement is fundamentally associated with the fact that the large oscillations in the transient can damage the system structure and the other component associated with the indirectly with the system. And whenever the transient is not dying out, and instead in some cases if it is continuously increasing, it is a threat to the operators and the life involved in the loop, and also with the component and the plant itself. The next thing is the stability of the system. So if the system is stable, definitely the transient response will approaches to zero with time. So if the closed loop is more stable, this means the transient response will approaches to zero quickly, and whenever the system is less stable, it will take longer time to reach to the time response will reach to zero in long time. So these topics we have already discussed. The stability of the linear control systems from the transfer function approach we discussed in the lecture series on the stability, and the topics were aligned with the textbook of the Norman Nice on control system engineering. So if the loop is stable, then fundamentally we discuss about this current chapter, the steady state errors. And the steady state behaviors become prominent whenever the transient response of the system die out or approaches to zero. So the performance of the stable systems normally is analyzed using the steady state errors of the system. Whenever we say steady state error, it means that when the transient response of the system is close to zero, how close is the output of the system to the desired output or to the reference input of the system. So this is the topic of the this chapter. So mainly we will be discussing the types of the errors associated to different type of input signals. When we say these different type of input signals, we means the standard input signal like the step input signal, the ramp input signal, or the parabolic input signals, and how with these different type of test signal the system steady state error will behave. So this topic we will discuss in these lectures. We will discuss the analysis of the methods developed for controlling these type of steady state errors. So when we say controlling, it means that how we can eliminate the steady state error. This means the error between the desired signal and the plant output becomes 0, or reducing it like within certain percentage. Of course, from theoretical point of view, it is not possible to completely eliminate the effect of the disturbances on the system. They will remain there, but we can reduce them to as minimum as possible. And in general application, the requirement is that the steady state error should reach to 10%. In many applications, it is required 5%. And for certain high performance systems like the nano positioning systems and the micro positioning system and IC manufacturing, there the positioning required less than 1% accuracy of the steady state error. So these type of things we will discuss in this chapter. Trade-off, like normally there is, if we improve the steady state error of the system, so during doing that effort, it is possible the closed loop system may become unstable. So it is a trade-off, like when we improve one performance index of the closed loop, the other is going toward the negative side. So there is always a trade-off because the requirements are contradictory to one another. So this type of thing, like when we say the system should respond quickly, and so this means that we have to make the closed loop, we should respond very quickly, but in that case the transient of the system will have some oscillations and the transient will take longer time to die out. So these type of trade-offs we will discuss over here. The steady state error specification, when we want to make the error is very small, so normally the gain of the closed loop is increased, but increasing the gain of the closed loop can make the system oscillatory, and also in some cases it can make the system unstable. So there is always some trade-offs over there. So the stability, steady state error specification, and the transient behavior of the system normally are the trade-off of the steady state error. So these are the topics of this introductory part of the first lecture. So when we will discuss about the steady state error, the abbreviation we will use for this is the SSE. So the reference input to the system, sometimes we say to this the desired output of the system is R of t, and actual output of the system is C of t. So C of t is the output of the plant and R of t is the reference input of the plant. Like if I want to sketch it, it will be something like this. Like here is the R of t is the input, here is the transfer function g of s, and output of the system is suppose y of t. Here we say to this y of t as a C of t. So when we say steady state errors, error of the system, so we mean the E of t is equal to R of t minus C of t. So this is the error of the system. So for the steady state error, when we say, so fundamentally we mean the difference of the reference signal or the desired signal and the plant output whenever time tends to infinity. So this is the steady state error. So fundamentally we say the steady state error is the error of the output with the reference input or the desired input whenever the time approaches to infinity, and generally it is required that this should be equal to 0, but in many cases it may not be possible to get exactly 0, but within certain percentage like 10% or 5% of the total value can be achieved. So this is the type of things we will be discussing. In steady state analysis, the input signals are pre-selected and are called the test inputs, and these test inputs are the standard signals. So first of them is the impulse, and we have discussed that what is the Dirac impulse. If you have some doubt on Dirac impulse and you think like it is not clear to you, it is better to go to chapter 1 of the book. There the discussion about the Dirac impulse is given in detail. Then the step input we will be discussing briefly. On the next slide we will discuss this, that what is the step input, though we have discussed this in detail in chapter 1 and 2. Ramp input, the parabolic input to the system. So these are the standard signals used for analyzing the steady state error of the stable systems. So here I will briefly discuss the basic standard signal for testing the control system loops. So first of them is the, you have studied this before and you should be knowing it. What is this waveform? It is 0 before the time 0, but just at 0 plus it becomes from 0 to some value. So if it goes to any higher value, we say that it is the step input or step signal. But if this step is of 1 unit, we say it is unit step. So normally we consider it as a step function or a step signal. But if the magnitude of this step is 1, we say it is unit step. And whenever it is unit step, this means here it is 1, and then we say it is unit step function. So either it is unit step function or unit step signal. So what is the physical interpretation of this signal? So physically it is originally a constant position, like a set point. Suppose we set a point at 25 degrees centigrade, so then it remained 25 degrees centigrade. So this means that the value is constant, so the position is constant. Or if you set in your car using the cruise like 80 km per hour, so then 80 km per hour is a set point and which remain the fixed value. So to such things, like at a certain time we change it from one value to another, like suppose some value was 60 km per hour and we change it from 60 to 61 km per hour, and then it remained constant. So the physically it is a constant or the position function. So constant position we say. In time domain normally we write it as u of t, and whenever we write u of t, this means it is unit step function. No need to write 1. This one just I write here to emphasize that the magnitude of the function is 1. But if it is other than 1, we write here number. Like if it is step function 2.1, we should write it. But if it is 1, then we write only u of t, and u of t represents the unit step function. And of course, the Laplace transform you have studied for this. And what is this? Can you write it? Write it with yourself. What you got? Did you get 1 over s? Yes. So before getting the answer here, written answer, it is better for you first go and practice it. Check whether you are getting 1 over s, the Laplace transform of u of t. Then you see here, so it is 1 over s. Then we have the second function. What we say to this function? Can you say it? It is constantly increasing. What can be this function? So we say to this ramp function. So ramp function is normally, we say to this ramp, and the slope of this is 45 degrees. This means the slope is equal to 1. And in this signal we say constant velocity. So the previous one was constant position. This is the constant velocity. This means if the position of the system is changing, so then this is the derivative of the constant function, or integral of this function. It is the integral of the position value, which will be going like this, and to this we say constant velocity, and we represent this by tu of t. We say that this equal to tu of t, and tu of t, what will be the Laplace transform of this? You should stop here and check what is your answer. And before going forward in this video, you should stop the video here and then see whether your answer is matching with my answer. So here you will be getting the 1 over s square. So 1 over s square is the Laplace transform of the tu of t. Tu of t, we say it is a ramp function. So the signal starts at 0 and then constantly it is increasing. And then we have the ramp function. Ramp function is the fourth signal we are using. On this page we are showing 3. The unit step function you can look in chapter 1 and chapter 2 of the book. So if we write here ramp function, so ramp function is integral of this one, and it is normally representing the, if we say, constant acceleration function. So here it is the parabola, and this is the constant acceleration function, and we say that it is equal to half t square u of t. If you are looking, this function is integral of this one. One question may come in your mind, and can you answer that yourself or search for it, why it is like this? Normally, position is the integral of velocity, and velocity is the derivative of the position, and acceleration is the derivative of the position. But here the constant acceleration is integral of the constant of velocity, and constant of velocity is the integral of constant of position. Is it not exactly opposite? So can you think why they are? Can you find an answer for that? So this question I put for you. Search for this on internet. Can you answer it? Okay, what will be the Laplace transform of t square upon 2u of t? So here you should again stop the video, do it yourself, and then check what answer you are getting. Okay, so you will get over here 1 over s cube. Originally all these details we have done in chapter number 2 of the book, and the slides are already available on the Moodle. You can see over there. So even then, if you have some questions, you can just email me through the Moodle and I will answer you.